Welcome to lecture 37, Fourier series and separation of variables, the general series, and solving Laplace. So we're going to start by looking at the general Fourier series. Last time we showed it in the exponential form. F of theta was the sum n equals minus infinity to infinity a sub n e to the in theta, where a sub n was equal to the integral from minus pi to pi d theta f of theta e to the minus I n theta, the whole thing divided by 2 pi. Now, in the case that we were looking at, theta was the polar angle, and we were looking at functions on a circle, so there was a natural periodicity of 2 pi, but there's nothing sacred about that interval length. So to be more general, we suppose that we have a periodic function in the region between minus L less than or equal to t less than or equal to L, and then the Fourier series becomes f of t is equal to the sum n equals minus infinity to plus infinity a sub n e to the I n pi t over L, and a sub n is equal to 1 over 2L, the integral from minus L to L dt, f of t e to the minus I n pi t over L. So it's easy to make this change from an interval that has length 2 pi to an interval that has length 2L. Now, there are two very special cases that are worthwhile really focusing on. The first one is what happens if the function f of t is even. Well, if it's even, I can take the definition of an and I can do the integral between 0 and L as opposed to between minus L and L. Because f of minus t is equal to f of t, I get the two exponential terms as shown in the square brackets, and you immediately can recognize the sum of those two terms is just 2 times the cosine of n pi t over L. So I can replace that by the cosine, and the factors of 2 cancel upstairs and downstairs in the prefactor for that integral. Now, because it's a cosine here, if I take n goes to minus n, you can immediately see that an is equal to a minus n. And so that is one of the results that we get for the Fourier cosine series. And to summarize what f of t becomes, we're going to slightly change our definitions. We're going to look at little a n, which is equal to 2 big A sub n. And then what we can find is f of t is equal to a0 over 2 plus the sum n equals 1 to infinity little a sub n cosine n pi t over L, where little a sub n is 2 over L, integral from 0 to L dt f of t cosine n pi t over L, under the understanding that f of t is an even function. And this result is called the Fourier cosine series. All right, so we just did the even case. Now let's take a look at the odd case. So for the odd case, we're going to have f of t is equal to minus f of minus t, and a sub n is equal to that integral that is shown to you there. We're going to restrict the integral between 0 and L, and now because f of minus t is equal to minus f of t, we'll get a e to the minus I n pi t over L minus e to the I n pi t over L, and that's proportional to minus 2I times the sine of n pi t over L. And in this case, if I let n go to minus n, you can immediately see that an is equal to minus a of minus n. So let's put this together, and we're going to define bn to equal 2I times a sub n. And f of t is the sum n equals 1 to infinity of bn sine n pi t over L, where bn is equal to 2 over L, the integral from 0 to L dt f of t sine n pi t over L. And this is called the Fourier sine series. So now for a general function, it's neither even nor odd, so we have to add both even and odd pieces. And so f of t will equal a0 over 2 plus the sum of the cosine series plus the sum of the sine series. And that result is called the Fourier series. All right, let's take a look at an example. Let's look at an even function that is shaped like a sawtooth. That is this shape here. It's going to be 0 and have its minimum at t equals 0. And let's look at the n equals 0 coefficient. It's 2 over L, integral from 0 to L dt of t, but that integral is just equal to L squared over 2, so we find a0 is equal to L. Our next step is to look at n not equal to 0. In this case, we have this cosine in here. We have a t times a cosine, and the best way to handle this is to do integration by parts. I'm going to differentiate the t, which means I have to integrate the cosine, and so the Boundary term is going to be t L over n pi sine n pi t over L, which has to be evaluated between 0 and L, minus L over n pi, the integral from 0 to L dt of sine n pi t over L. Now, if you look at the first term with the boundary term, when t is equal to 0, it's of course equal to 0, but it's also equal to 0 when t is equal to L, because sine of n pi is equal to 0. So the boundary term vanishes, and now I have to do the integral of a sine. That's going to be minus a cosine, and I get the factors in front. I get the 2 over L from the prefactor for the integral, and then I get an L squared over n squared pi squared times the cosine of n pi t over L evaluated between 0 and L. Now, when t equals L, I have cosine of n pi. That's equal to minus 1 raised to the nth power. And when t is equal to 0, I just get 1. And so we get this final result for the ANs, 2L over n squared pi squared minus 1 to the n minus 1. Notice if n is even, that first term is 1, and 1 minus 1 is 0. If n is odd, the first term is minus 1, and minus 1 is equal to minus 2. So these coefficients are non-zero only in the case where n is an odd number, and I'm going to write that as 2n plus 1, and then I get minus 4l over 2n plus 1 squared pi squared. So let's plug this into our series to find out exactly how we express this even sawtooth. It's going to have an L over 2 from the A0 over 2 term minus 4L over pi squared, the sum n equals 1 to infinity, 1 over 2n plus 1 quantity squared cosine of 2n plus 1 pi t over L. And that is what we get for the even sawtooth. The next case we're going to look at is the odd sawtooth. It looks very similar to the even one, except it's an odd function, and so the sawtooth part looks like it has a longer period, but it's really the same period. And now we're going to, the difference here is, of course, that it's discontinuous. So now in the odd case, we're going to get Bn is 2 over L integral from 0 to L dt t sine n pi t over L. Once again, we integrate by parts, 2 over L minus t L over n pi cosine n pi t over L, evaluated between 0 and L, plus L over n pi integral from 0 to L dt cosine n pi t over L. Now I look at the boundary terms. Of course, the term at 0 is 0. The term at L is equal to minus 1 to the n times L squared over n pi. And then I have to multiply it by 2 over L, so I get 2L over n pi times the minus 1 to the n. And because there's a minus sign in front of it, we can absorb that in and make it minus 1 to the n plus 1. All right, the integral terms, these integral to integrate the cosine, I get a sine, and so I get 2L over n squared pi squared sine n pi t over L. I evaluate that at L, I get 0. I evaluate it at 0, I get 0. And so actually it's just the boundary term that contributes in this case. Now notice this boundary term goes like 1 over n, not 1 over n squared, which is what we got in the other case. Now when a Fourier series goes like 1 over n, it's kind of marginally convergent. And it's that marginal convergence that allows this function to exhibit the Gibbs phenomenon that we were talking about before. And indeed, this kind of odd sawtooth will exhibit a Gibbs phenomenon. And so you will be able to see that rather clearly if you look at the Fourier, if you look at plots of the Fourier series where you stop the summation at some particular value of n. Okay, so put this all together. The function f of odd sawtooth is just minus 2L over pi, minus 1 to the n sine n pi t over L. There should be a 1 over n in that. That's a typo in the summand. There should be a 1 over n. And aside from that, everything else looks like it's correct to me. So just bear in mind, 1 over n in that summation. Otherwise, that summation, of course, won't converge. Okay, that's our odd sawtooth. Now we're going to take a look at an example of a Laplace's equation, or a Laplace-like equation. It's really a wave equation. We're going to look at a vibrating string. The string is going to be attached on two ends at 0 and L, and we're going to use the symbol u of x and t to denote the displacement from a horizontal line. The figure has a y of x and t. We're going to use the symbol u, as the book does. And this satisfies an approximate differential equation, which is given by t times the second derivative of u with respect to x is equal to rho times the second derivative of u with respect to t, where t is the tension in the string and rho is the mass density. Now, the left-hand side of that function is like a potential energy, and the right-hand side looks like a kinetic energy. And so this equation looks like the potential energy is equal to the kinetic energy. Now the boundary condition is that the string is attached to the walls. We already talked about that, so that means u of 0t and u of lt are equal to 0 for all times. And we're also going to assume that there's an initial condition. So u of x0 has some shape, f of x, and du by dt of x0 has a different shape called g of x. And what we'd like to do is we'd like to say if we know what those functions are at one particular time, let's go ahead and figure out how we find it for all future times. So to solve this problem, we're going to use separation of variables. You've seen it before. We're going to take u of x and t and write it as the product of x times t of t. Don't confuse this capital T with the tension in the string, which is also given by a capital T. You should be able to sort through both of them in terms of the context. And in particular, wherever capital T of t appears, we're going to try and put in the argument of t so that it's clear that that's the function and not equal to the tension in the string. All right, so after we plug that in and we plug it into the differential equation, we're going to get the second derivative of x divided by x is equal to rho divided by t, the second derivative of t with respect to t, and that whole thing is going to equal minus c. Okay, so how do we solve that? Well, it's just exponentials. So we get a e to the I alpha x plus b e to the minus I alpha x plus little a e to the I beta t plus big B e to the minus I beta t. Now let's plug in our first boundary condition. When x is equal to 0, this thing must vanish for all t. And when x is equal to L, this thing must vanish for all t. And what we find when we do that is the first one is going to restrict a plus b equals 0. And the second one is going to tell us that sine of alpha L must equal 0. So if sine of alpha L, where alpha is square root of c, is equal to 0, that means alpha is equal to 1 over the square root of alpha L, which is just n pi over L. All right, so we're going to define a frequency to be pi over L times the square root of the tension divided by the mass density, so that we can write u of x and t as the sum n equals 1 to infinity sine n pi x over L times these two unknown coefficients and functions, little a sub n e to the I n omega t plus little b sub n e to the minus I n omega t. Now we still haven't put in our initial condition, so we're going to set t equals 0 to find a condition that the a n's and the b n's must satisfy to give us f of x at t equals 0. And also we're going to look at the first derivative, or the velocity at t equals 0. And we're going to do that by differentiating under the integral sign, and that's supposed to equal g of t. So we have to set those boundary conditions in order to get this to get to the final solution that we are going to get for these equations. Okay, so f of x is of course going to equal an plus bn times sine n pi x over L, summed n equals 1 to infinity. And g of x is going to equal that sum times I n omega times an minus bn. And we have to determine what are the Fourier sine series of f of x and g of x in order to solve these equations. So the first thing we have to do is determine those Fourier sine series. I'm not going to do that for you here in this lecture, but you're going to have an exercise where you do it in class as the problems that are accompanying this lecture. So you're going to get an experience with doing that yourself. And the only thing left that I want to point out is this series that we get for the u of x and t is then the solution of the problem in terms of a series solution. And if you go on and look at the solution of Laplace's equation, or things like wave equation or other things like that, in many different contexts, this is how all of these kinds of problems are solved. The geometry of the problem and the constraints determine what the Fourier-like series would be. It's not always a Fourier series. And then the boundary conditions are incorporated in the way in which we incorporated them here to allow you to then solve for all the different coefficients and get the final functional form. But the end result is going to ultimately be a series, and there's not very much you can do with the series unless you can sum it up, at least approximately, or partially on a computer up to the point where it converges, and then plot the results of the series to get an idea of what the actual function itself looks like. Okay, with that we are finished with lecture 37.